say it's one of the most beautiful cities in the world. It's certainly a lot better than 1 kilometre under the Queensland desert. So my talk today is on, extensively in the program, of course, the advances in technology and science, but I've changed the name somewhat. I'm going to call it the start of science, and I'm calling that as a nod to both Horgan, who of course, as you know, wrote a book called The End of Science, which a lot of people think is profound, and I, like others, think it's profoundly wrong. But he also as a nod to some of the cosmologists who've made statements here, who pointed out to us, of course, that there's a lot more in the future in time than there is in the past. When we go back 13 odd million years to the Big Bang, but look forward to the heat death of the universe, we've got a long way to go before that happens. So there's a lot of time ahead of us. And if you think that science has only done its thing in that last fraction of a second, comparatively on the scale, imagine what it will do in the next 13 billion years of actual real operational time. But mostly I'm going to talk about technology and why it's important to understand and characterize the nature of the developments that are taking place in technology. And to do that, to some degree, I also have to go back to the past. The other thing that I want to impress on you is that this time we have now is a unique and special time in history. Now, of course, scientists don't like to talk about unique and special times in history because there's something a little bit weakly anthropic about it. They like to talk about, they say that any time is unique. Any time. And of course, you go back in history, you talk to the Romans, you talk to the Ming Chinese, and they all say their time in history was, of course, unique and special. But our time really is special. This time now, the decisions that we make, and some of the people in this room are making those decisions, the decisions that we make in these months, these years, will affect the future of humanity forever. So it's important to maintain the dialogue so that we can form a kind of democracy of ideas and hopefully make no mistakes. So let's get started. Firstly, a bit of my background is, as we said, I'm a field roboticist. Now what this means is I don't make robots like this one, which is creepy, or like this one on the right here, which is really cutie. The robots that I make are the sort of robots that you guys will never, or very often not see, or very seldom see. Specifically, they are your standard field robots. Like that. That's one of my robots there. That's a 55-ton load-haul dump vehicle. That's a fully automated vehicle that's used underground mines, metalliferous mines, scoops up ore, travels a few hundred meters, dumps ore in another place. It does it 24 hours a day, 7 days a week, 365 days a year, with a little bit of time off every now and then for petrol, oil, and maintenance. That system is, of course, widely in use, or systems like that. Invisible to you. It's narrow AI by the standards that have been discussed in this room. The environment it operates in is relatively structured, but it does change. You'll have rock burstings burst out of the ground or out of the side because of the high pressures when you're a kilometre underground. You've got high dust. You've got all sorts of problems that make the environment very difficult to operate in as a human being. And hence, automation is obviously being targeted for that particular environment. Now, before I move on, I just want you to understand the scale that we're talking about there in terms of finances, for instance. These are big systems. They're a very expensive system. But every time that system scoops up a bucket of ore and puts 20 tons of ore in that bucket, if that's, say, a copper mine, that bucket load of ore is worth about $2,000 on a standard mine. And it will pick up one of those every 3 minutes. And mines like Freeport, etc. in New Guinea, they'll be running 20 or 30 of those machines at the same time. So there's a lot of money in the industry. You can see that those things can easily amortize a capital debt of several $1 million within just 1 year of operation. Pay it back. And at the end of the time, those machines are all self-insured and they will be written off constantly. They get destroyed, they fall down big holes. But, so that's the environment I come from, and I've been automating systems like that for many years now. And so I've had to look at the process of automation itself. What happens when we automate a system? How do we go about automating a system? What sort of analyses do we have to do? And in order to do that, I've had to firstly analyze what it is to be human, what the problems are associated with being humans in that operating environment, and try and break things down to their lowest common denominator. Now, being an engineer, the first thing I do is a bit of a back-of-the-envelope calculation, and that is, you look at your variables, you decide, is this thing reasonable? Now, the first question I say is, when I want to automate systems in line, I go and look and see what's off the shelf, because off-the-shelf equipment has low maintenance, it's much easier to operate with, so you generally get off-the-shelf components and glue them all together to create your AI system. That's a Caterpillar low-haul dump vehicle, German sensors, German computers, etc., etc. So the first thing I do with the back-of-the-envelope calculation, I say, well, will technology continue to improve? Will the various parts of this human capability envelope, which I'll talk about later, will they be able to be subsumed by technology in the future? So the first question I ask is, will technology keep advancing? And of course, that would be an odd question for people in this room, because all of you, I would suggest, would say, yes, obviously, technology is obviously increasing. But I have to tell you that that is not a perception that exists out necessarily in the real world or in the other world. That unfortunately there is a kind of palpable disappointment in part of the world regarding technology. People are saying, look, we haven't gone back to the moon, the Concorde crashed, never got up again, we've still got inflation, stagflation, we've got all sorts of economic issues, we've got we're throwing out a whole doctrine, we're trying to treat a Keynesian liquidity trap with 1930s austerity measures, and everything is going wrong. We're throwing out the lessons we've learned, and science is not stepping up to the plate, except, of course, in one area, and that's IT. Now, this is very important because when say, Aubrey goes into a banker and he says, look, I want $850 million to fund my, I want to make everyone immortal. So I want $850 million. And of course the banker will look at that guy and he'll say, that's a good idea. He likes the idea personally, but of course he's thinking in the back of his mind, where's my rocket belt? Where's all these promises that I saw when I was young and that have not manifested? And of course we have to understand this perception. There's also another problem with finance capitalism that I will, I'll get onto later. So, is technology advancing? Now, the simple issue is that if you look at some of the objective evidence, it's not. This is Huber's fairly famous graph. He's showing that, in fact, innovation is actually declining. That as time has progressed, things have gotten worse. We've become less innovative. Another similar one is the number, and more objective evidence, the number of patents that have been issued have actually dropped from the 1910s, 1915. Now remember, that was the time of Einstein, before that was a very significant time in history. Those people were doing seminal works. Electronics, the first electrical theories were coming, people started to use Maxwell by then, and the Wright brothers were flying aircraft. That was a fantastically active time. And beyond that, of course, the number of patents per individual has dropped off. And there's a lot of reasons for this. Of course, some of those are simply because that now a lot of things are developed by institutions rather than individuals. That there's a lot of knowledge out there. It's a lot harder to be a polymath in our society than it was to be a polymath back in the 1900s. There's a lot more to know. But superficially, there is evidence for it, a drop-off. And that's why people like Horgan wrote their book, The End of Science, positing that it's all been done, it's all just going to all fizzle out, string theory is going to go away, and we're all going to end up in some kind of status. It might be nice. But of course, the internet kind of proved them wrong. And if you look at other technologies, which we'll do now, you can see that even though the number of patents has dropped, and innovation may actually be individually in decline, because of the augmentation that has been done by technology, by IT technology specifically, we're still seeing an increase. Now look, that graph there, which I pulled up last night, is showing the development of the internal combustion engine. And you can see the blue line at the bottom is actually the steam engine. And you can see that on the left we've got watts per kilogram, so it's basically a power to weight ratio. And on the center, the red line, extending up to the right, is your internal combustion engine development. You can see that's fairly robustly up. There's a bit of a drop between when they were doing the muscle cars back in the 1960s, because they were looking for more noise and power and things, and then we had the oil shock in the 70s, and people said, oh no, we'll calm down on that. Remember, high power to weight ratio doesn't mean good fuel consumption. So you can see a fairly robust increase in that fairly ubiquitous technology. We see it everywhere. But most interestingly on that, if you look at around the 1900s, see that little vertical uptick there? That is flight. What happened there was Wilbur Wright and Whitehead and various others were all saying, hey, these internal combustion engines, they're great. They've got a really high energy within this fuel, much higher than we can get in a steam engine. They're applying Carnot's theories from 100 years before, and they're saying, hey, we can do something with this. And so they picked up those internal combustion engines, modified them in their own garage, and created, and that's why you have that sudden vertical spike. The enabler existed, but then people saw, hey, we could do that with this enabler. And you'll find that throughout technological development, this is a common practice, that the enablers usually pre-exist the invention. And in the words of Karl Popper, we do not know today what we will discover tomorrow. And that's also part of the explanation for why we don't have our rocket belts. Because those people were trying to predict ahead. They predicted things based on their own perception of technology, which were outside of economics and science. I mean, we might still get our rocket belts, but it's requiring a few technological leaps to get that far. Let's move ahead. So, where's the decline in innovation? One of the major things is that it hasn't really happened. It's actually all gone here, to things like these iPads. And all those little icons there, which are, they represent intellectual property, work done by people to develop those things, and they are in fact unpatentable, so they don't show up on the graph. What's happened? In the same way that when the Wright brothers crossed that threshold and developed airplanes, which then developed rotary engines and developed turbines, gas turbines, and that whole area of flight opened up, the internet and networks and computers, based on Moore's law, of course, have also now opened up an entire domain of invention and discovery, which do not feature in the graphs of people like you. All right. What I want to move on to now is now going back in history and based on the work that I've done in automation. At a very fundamental level, nature has designed us to perform tasks in the world. It's done that by a process of evolution. And we know that that's not infinite. There was no reason that nature in its ruthless search for efficiency would need to make us infinite. It made us what we needed to be to do the job. We became what was necessary to do the task at hand. The consequence of this is that we have a lot of capabilities. We have visual acuity, we have audio acuity, we have tactile acuity, we have mental processes that can be applied to things. Our bodies have certain constraints based on temperature, based on pressure, based on the air that we breathe. We have a certain amount of work output that we can do over a certain period of time. And if you accumulate all of those fundamental bits of knowledge, you have a capability matrix of the human being, which is absolute. Now, of course, there's sexual dimorphism, there's racial dimorphism, there's a whole lot of different issues here, and I'm blurring it and I've oversimplified it greatly. But I just want to make the point. This is one single graph to show you what we're looking at, where you can see watts on one hand, that's energy output, and temperature on the other side. Now, of course, this is very important in my work because some of those deeper metallurgist mines will be operating at 50 degrees centigrade with a wet bulb humidity of 100%. So it means that you cannot physically get cool, and people will die in that environment. So therefore, it makes them right. Now, a couple of other things. Of course, you realise that there's things like wind chill factor. If you put air around the thing, there's the amount of work that the person does affects it, but that's just one single snapshot. And of course, I haven't even touched on hysteresis. If you put a person in 60 degrees like that, he's not coming back. Right? He's going to die, and so the curve doesn't go back the same way. There's a massive hysteresis. It drops to zero, and that's the end of it. If you take these capability matrices and join them all together, you'll end up with in a multi-dimensional space, which is what we call an isosurface in multi-dimensional space. I've done it in 3 dimensions there, or 2-dimensional representation of 3 dimensions, just so that you can see what we're referring to. And this capability matrix is the human being, is the basic human being as you come out. It is an expression of your genetic code. It's not your genetic code, it's an expression of your genetic code. And what we do as humans, of course, is we augment our matrix by adding things like clothes, by adding things like tools. And these augment our capabilities in some way so that we can then perform on whatever the domain of the job space is, which is hopefully smaller than our capability space. So what happens is we match our capability space over the top of our job space, like that, and if there's a mismatch, like in that case, then we have to augment ourselves in some way. So, and we augment ourselves by, say, protective clothing, or by using tools, or by training, some sort of cognitive advancement. So it's necessary to augment ourselves, to give ourselves a better, if you like, fit. And in the mining industry, this is some of our augmentation. But in the real world, this is some of the tools that have been used to augment over the years. We've had spear points and things of that nature. Now, most significantly, and writing, of course, mimetic augmentation. Most significantly, one way we augment ourselves is by multiplicity. We send lots of people to do the job rather than one person. And the net result is that this collective effort increases our capability space so that we can actually perform the task. The long-term consequence of this, of course, has been that over time, as we've been augmenting our capability space, suddenly we find that one person can be augmented to do the work of 20 or 30 or 40, and so we have massive unemployment as it took place in the 1850s due to the Industrial Revolution. Now, it's important to realize that this is augmentation. It's not machines taking your job. It is one person augmented with a machine taking your job, or taking the jobs of many others. Now, initially, there was enough elasticity for those people to go off and work in some other jobs, but that elasticity is running out because the assault that we now have through technology is, through Moore's law, is on our cognitive ability. And the last 2 slides, if you look up, that is our current supercomputer performance. If we look at where we are, ring the bells, hallelujah, we are there. So the current range of supercomputers are now operating within that 0 to 10 petaflops, which is what is projected that the human brain is able to achieve. And a similar one, if you look at the cost per gigaflop, you can find again that we have now passed on the downward scale the cost of having children. In other words, we can now, it costs about $500,000 to take a kid, grow them up, put them to university, and before they go into the world and start being productive. We have now passed that threshold. For that $500,000, we can now build a computer that has the same, let's say, hardware capacity. We haven't got software yet, but people like Ben and Co are working on that. All right, that's all we have, unfortunately, time for.